Hi, in this video we're going to be looking at integrating exponential functions and functions that lead to us getting natural logarithmic functions. So this is pretty simple. I'm just going to do a few examples. We know in the past where we have the derivative of e to the x is e to the x, so we've studied that one. So understanding the fundamental theorem of calculus then allows us to make this assertion that the integral of e to the x is e to the x plus c. Further, we understand this rule about the derivative of e to the f of x. So when we have, say, e to the 4x, we know that the derivative is 4e to the 4x. So working backwards then, if we're integrating functions that look like this, the integral is e to the f of x. So if you can recognize that a function is in the form derivative times e to the original function, you know what the answer is going to be. But most of these questions like this I'll do using substitution. So let's have a look at a few examples. The integral of e to the 4x. Here's the reverse chain rule coming in here. The integral of e to the 4x, I know that the answer is going to have e to the 4x in it. I know that's true. But remember, when we do the derivative now of that function, we get e to the 4x times 4. So because of the chain rule there, we've multiplied by 4, so we've got to take into account that we're going to have to multiply by 4. And I'm going to adjust for that by writing that there. So that's the reverse chain rule coming in there. And now if I do the derivative of that function there, I will get e to the 4x. Part B is one of those ones I said, if you can recognize that we want a function in the form the derivative times e to the original function. So if we had it in this form, then I know the integral would just be e to the x squared plus 4 plus c. But we want the derivative at that thing right there has to be the derivative of this function here. Now in this case we're not quite there, we want 16x, so I'm just going to adjust for that and put an 8 out the front. And now that's correct. If you look at this step here, we now have exactly what the question says, that is 16x e to the x squared plus 4. I've taken the 8 out, so now I can just bring the 8 in, and now that's the answer. The alternative here is to use substitution. If I say u is equal to x squared plus 4, and typically in these examples, if you make the power of e u, if that's your substitution, that's the way it works. So du dx in this case is 2x. So rearranging that means dx is going to be du over 2x. So we go back to our integral now. We've got the integral of 16x e to the power of u, because u is x squared plus 4, and dx I'm going to replace with du over 2x. You can see now that the x's cancel, and we've got the integral of 16 e to the power of u du, and that's just 16 e to the power, sorry, big button, it's not 16. A bit more cancelling, 2 goes into 16 8 times. So we get the integral of 8 e to the power of u with respect to u, that's just 8 e to the power of u plus c, which of course is 8 e to the x squared plus 4 plus c. So we get the same answer as what we got before, just using substitution. Okay, so now for integration giving logarithmic functions. Same thing. Recall that when we had y equals ln x, then the derivative was 1 over x. And further to that, if we have ln f of x, then the derivative was the derivative over the original function. So working backwards now, if we have functions in this form here, derivative over original, the integral of that function is ln of the function on the bottom line. That's a really important one to remember, and you'll see me do a few examples using that form there. So the integral of 5 over 2x. Now recall in the past, if you'd have tried to do this one, we can take the 5 over 2 out, got the integral of 1 over x. Now if you'd use the old rule, that's x to the minus 1 there, add 1 to the power, divide by the new number, you see that we're in trouble there. X to the 0 over 0. That's why that rule for polynomials does not work when the power of x is -1. The answer to these is, the integral is ln x. Okay. In this example, again, what we want to do for these ones is write it in the form the derivative over the original. So the form that I want is that. That's what I want to get. If I've got it in that form there, then I know that the answer is going to be ln x squared plus 1. I'm going to put in some absolute value signs in there for now. But we had 10x on the top, so I'll need to adjust for that by writing a 5 at the front. Okay, so write the integral that you want, so the rule works, derivative over original, and then adjust it with a number at the front, so you've got the same as your original question. So there's my answer to that one. Okay, for A here, the integral of 6 over 3x plus 1, any linear terms on the bottom line here, you know it's going to be an ln. You know the integral is going to be ln. There's a couple of different ways of approaching A. One way I can do it is this. Put the 6 at the front, and I've got 1 over 3x plus 1. And now I'm going to use the reverse chain rule again. So I'm going to do the integration. Now let's think about this. Don't worry about the 6. Let's just not worry about that 6 for a moment. Let's just focus on the 1 over 3x plus 1. If I was to do the derivative of this function right here, we would say it's 1 over 3x plus 1 times 3. Now we need to allow for the fact that we're timesing by 3, and the reverse chain rule says that we'll be putting a third at the front there. Now that's correct. If I differentiate this function here, I'll get 1 over 3x plus 1. 1 over 3x plus 1 times 3 divided by 3. That works. But of course, we've got the 6 at the front here, so we end up, 6 times a third is 2. We end up with 2 ln 3x plus 1 plus c. Now, the other way of thinking about this problem is to think of it as we want it in the form derivative over the original function. And I know what the answer is for those ones. So in this case here, the bottom line is 3x plus 1. I therefore want the top line to be 3 so that it fits into that form. But we actually had a 6 to start with, so I need a 2 out the front to adjust for that. Now that looks exactly right. So now it's in the form I want, 2 ln 3x plus 1 plus c. So it doesn't matter which way you do it, you're going to get the same answer. Okay, let's look at part B. Part B says the integral of 8 sine 2x over cos 2x. Okay, this does not look like it's going to have anything to do with a natural log integration, but if it's in that form, derivative over original, that's what we actually get. So, what is the derivative of cos 2x? We know the derivative of cos 2x is going to be -2 sine 2x. So that's the format I want, and I've nearly got it. All I need to do to adjust for the number at the front is write -4 at the front, and then I've got it. Then I've got it in the form derivative over original, so my answer is -4 ln cos 2x plus c. Let me just say a word of why I'm putting these absolute value signs. If I'm integrating 1 over x, that is this function here. So I might ask the question is, what is the value of that integral there between -1 and -2? I might say, what's the value of that integral there? So that's fair enough. That's just the area under the curve, between the curve and the x-axis. So I could do my integration, ln x between -1 and -2, ln -1 minus ln -2, and hopefully you'll see there's a big problem here. ln of -1 is not defined. In fact, natural log values or log values of negative numbers are not defined. So we're into a problem here. What this formula allows me to do is just say, well, that's going to be the same as the area between 1 and 2 there. So if we use the absolute value of x now, we now get ln1 minus ln2, which is the value that I can work out. Okay, so or in this case it's going to be the other way around, it's going to be ln2 minus ln1 because we've got the 2 bigger than 1. So you can see that putting those absolute value signs in there is going to help us. Remember, if we're looking at the ln function, it's going like this, the natural log function. So it's only defined for x values greater than 0. So when we're dealing with the integrals with ln in them, we need to only be talking about positive values, hence the absolute value signs when we do these integrals. What I can do is multiply out the brackets. E to the negative x times e to the x. The bases are the same, so we add the powers. Negative x plus x is 0, so that is just 1. And now we've got a simple integral that we can do. The integral of e to the negative x is negative e to the negative x plus c. Another one that doesn't look like this is if we do the integral of tan x, which is sin x over cos x. Remember I said we want to have it in that form, derivative over original, so that is the form that we want. I adjust it by putting a negative at the front, and now that's the form we want. The derivative of the bottom divided by the bottom line. So negative ln cos x plus c is the integral of tan x. This one here you're certainly going to want to do using substitution. And like the other ones, you're going to use the substitution of if there was a square root sign there, you just had that question there, you definitely want to make your substitution u equals 1 plus e to the 2x. Okay, in this case it's power of 5, but that is definitely where you want to start for doing that substitution problem.